Hello, this is our Machine Learning for Virginia project, and Connor Goodall, Ben Osborne, and myself chose to focus on finding ways to apply machine learning to make the community of Charlottesville safer. So UVA students, we get these emails from Timothy Luongo saying community alert, some kind of crime, whether it's shots fired or burglary, or sometimes even tragically you see in the subject line rapes occur in our community. And it makes us kind of question when are we safe and how are we safe and where can we be to be safer? How can we reduce these, avoid it? And unfortunately, our project got much more real this semester when the lives of Devin, Lavelle, and Deshaun were taken from us on our grounds. And we want to be able to avoid further tragedies in the future happening to TVA students. So for data aggregation, we're fortunate enough that the city of Charlottesville provides public crime data, which is categorized. You can see here the offense has a label as to what kind of thing occurred. And they had some kind of spatial location data given by the block number and street name, but it's pretty limited. And it also gave you the hour that the incident was reported. We thought that these features weren't quite enough, so we decided to do some feature engineering where we used the geolocation API for coordinates. We were able to take the street and block number and get GPS coordinates to do some mapping visualizations. And we also had to use the US Census data to kind of populate the street population densities to make our analysis more thorough. So here you can see just some instances of violent and nonviolent crimes in the community.
The experiments. So for the violent crime rate for each street in the city of Charlottesville, the experiment that we did was trying different types of regression models. The 8 different types of regression models that we used on the training set were linear regression, decision tree regression, random forest regression, stochastic gradient descent regression, support vector regression, lasso regression, ridge regression, and gradient boosting regression. For each of these regression models, their hyperparameters were tuned in order to create the best model for that type. To determine what type of regression model was the best to predict the violent crime rate, root mean squared error was used. Out of these 8 types of regression models, the random forest regression model was the best regression model with an average root mean squared error of 0.034%. This was due to the average distance between the predicted violent crime rate and the actual violent crime rate being smaller compared to the average distance for the other regression models. For the nonviolent crime rate for each street in the city of Charlottesville, the experiment that we did was also trying different types of regression models. We used the same 8 types of regression models from the experiment that we did with the violent crime rate on the training set. These regression models also had their hyperparameters tuned to make the best model for that type. To determine what type of regression model was the best to predict the nonviolent crime rate, root mean squared error was also used. Out of these 8 types of regression models, the decision tree regression model was the best regression model with an average root mean squared error of 0.49%. This was due to the average distance between the predicted nonviolence crime rates and the actual nonviolent crime rate being smaller compared to the average distance for the other regression models.
So now we'll get into the outcomes and limitations of our process and these models. So first, we'll start off with the outcome of the violent crime rate. And when we applied our model to the test set, we achieved very promising results with the violent crime rate error percentage at 0.016 between the predicted value and the actual. And here you can see on the side, it's just a visualization of the predicted crime rate given the area on the map within Charlottesville. So you can just see kind of exactly what we were predicting for each of these points. And then on to the nonviolent crime rate on the next slide. So there our final error was 0.85%. And so these low rates just indicate that our model was able to accurately predict the risk of violent and nonviolent crime in the various areas of Charlottesville. In terms of limitations, though, there are a few limitations on our methods and our analysis, including one that our data is only from the Charlottesville Police Department, not from the UVA Police Department too. A more robust study would probably fuse together data from both departments, but since the Charlottesville data set was larger, that's the one we chose to use. It just means that we don't have any information on the crimes that are within the actual university community on grounds. Two, our data has no information about how much volume, say from day foot traffic, each street in Charlottesville has, so it is difficult to establish causality. Are some streets actually more dangerous, or do more people use them during the day but not live there and just provide more opportunities for crimes? And then third and finally, this data is the crimes that were committed and reported, and does not have data on crimes that were committed but unreported. This causes the data to take on biases that exist in policing. And finally, so what we think we would do if we could move forward with this and do something more, we think that a logical next step could be to integrate our machine learning models with the UVA sponsored student safety app Guardian to provide students with transit mapping service that selects routes between destinations in Charlottesville, with the objective of minimizing estimated time of arrival and also minimizing the likelihood of a student in transit being subjected to crime. And yeah, that's it. This work has been a part of the Machine Learning for Virginia project at the University of Virginia. Thank you very much for listening.